Okay, so you see now it's recording. So what I'm going to start is chapter 1, and I'm going to talk about, so our focus now is quiz 3 and what is required to know for quiz 3. So before doing that, I just want to make sure that we have like the necessary knowledge for chapter 1, which is, first of all, something that is important is electronic configuration, and we need that when we talk about molecular orbitals and also writing different types of bonding between, like whether it's like alkanes, alkenes, alkynes. So we should kind of have like some knowledge of electron configuration. And in general, I have one of these handouts that the tutoring center gave us. So something that you should know, any element in the periodic table that, if you consider your periodic table be like this, at least the main group element, let me see if I can do this efficiently. So this is group 1A, 2A, and then we have group 3A, 4A, 5A, 6A. I mean, I didn't do a good job here. 6A, 7A, and then group 8A again. It's kind of like goes back to here, right? So here is like if you consider these main group elements, whatever the number is here is like main group element, that is the number of valence electrons. So in this class, we're mostly interested in carbon and carbon compounds, okay? So we are in group 4A, and here, if the other naming system is 14, because it's like counts from here, 1A, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? But when we are talking about main group elements, is the ones that I just wrote here, right? 1A, 2A, 3A, 4A, 5, 6, 7, and they have extra 3, 4, 5, 6, 7. Okay, I have like one extra, and this is 8A. So now remember that one thing that we talked about in the class at the beginning, which is kind of like review of Chem 101 or any chemistry course that you had, is like Lewis structure, which shows us how electrons are distributed in atoms, and then when we have Lewis structures, we can see how atoms bond together. So to write Lewis structures, we should know the number of valence electrons. And if you remember from like other chemistry courses that you had previously, when we write, when we look at each element is in periodic table, for instance, fluorine as an example, the atomic number is listed on top, and this number here is number of protons. But atoms as themselves, there are neutrals, and since protons have positive charge and they are neutral, it should be the same number of electrons for them to be neutral, okay? And they have negative charge. So this is a question that I ask my students in 101. I say, how many protons and electrons one fluorine atom has? And then we say atomic number is 9, so it's like 9 protons is also 9 electrons. And when we want to write electron configuration, we write F as fluorine, and we put valence electrons around it. And then we say fluorine belongs in group 7A, or like 17, right? So this is two ways to name it, but whatever main group element it is, it has 7 valence electrons. And the way we realize that is that if we have like fluorine here, and this is nucleus that has positive charge, we have like one shell here that had maximum 2 electrons, right? And then we had like second shell that had like 9, because 9 is total number of electrons, minus 2 would be 7. 1, 2, 3, 4, 5, 6, 7. And that is why the valence of fluorine is 7, because on outermost shell we have 7 electrons. So when we have like fluorine here, for Lewis structure, we put number of valence electrons around fluorine. So for fluorine, since the atomic number is 9, because fluorine belongs in group 7A, it has 7 valence electrons. And what we do, we put 1, 2, 3, 4, 5, 6, 7. And we do, fill them out singly first and then pair them up, right? And this would be Lewis structure for fluorine. And as we said, we had like an expression named kernel that I asked in like your homework quizzes, exams. So here, this fluorine, this symbol is kernel, basically nucleus and field shell electrons. So this is your kernel, and it's just an expression. Now let me do, for instance, another example. And this is like what we're really interested in this class, because we're dealing with carbon compounds. So any material that has carbon, most of the time we have hydrocarbons that have carbons and hydrogens. For instance, carbon belongs in group 4A, so it has 4 valence electrons. So we put 1, 2, 3, 4 electrons around it. And the other thing that we briefly talked about from Chem 101, or like previous chemistry courses that you had, was like ionic versus molecular compounds. So ionic compounds contain cations and anions, and cations, they have positive charge, anions, they have negative charge. And most of the time, let me just clear a space here. So most of the time, 99% of the time, cations are metals that lost electrons, and anions are nonmetals that gained electrons. And when we have an ionic compound, we have cations and anions. So atoms in ionic compounds, they transfer electrons. For instance, this, cation, for instance, sodium, it loses 1 electron, becomes Na+, and this electron that, sodium has lost, chlorine will gain that, and then has like negative charge, because electron has a negative charge. When atom loses 1 electron, it basically the charge becomes positive. But when anion gains electron, or like an atom gains electron, the charge becomes negative. And so most of the time, you see, I asked you whether we have like an ionic compound or not, or what type of compound you have, you look at the periodic table, and then you identify, for instance, NaCl, MgBr2. As long as you have metal in your structure, it would be ionic compound. But for molecular compound, you have like 2 nonmetals, or a metalloid and nonmetal. You don't have metal. The other type of bond is covalent bond. And in covalent bonds, atoms share electron. So for ionic compound, we said 1 atom loses electron, the other one gains it. But for covalent bonds, atoms share electrons. For instance, when you have like CH4, and I talk about how to write these structures, right? 1, 2, 3, 4, you write the Lewis structure for carbon, and you write the Lewis structure for hydrogen, which we have only 1 electron. And now these carbon and hydrogen atom, they share these 2 electrons. So we have 1 electron here, 1 electron here, the same thing here, the same thing here. So sharing of these 2 electrons we show with this line or dash. And now this carbon has like 1, 2, 3, 4, 5, 6, 7, 8. So it reaches an octet. So basically this carbon has all of these 8 electrons, and this hydrogen has these 2 electrons. They're sharing electrons. Okay, the other thing that we talked about in chapter 1 was that if we have like an hydrogen atom, and this is the Lewis structure, the valence of hydrogen is 1, and then it has only 1 electron too. And then we have another hydrogen, they form a covalent bond, you see. So here you have a bond between these two, and these hydrogens share electrons. So each of them now has basically 2 electrons plus heat. So you should remember that each of these are like hydrogen atoms, each of these. And then this is a hydrogen molecule, and this reaction is exothermic because it releases heat. Okay, now we're going to talk about the fun things that is kind of like more practical. So if you want to write Lewis structure of methane, I just told you that you put like 4 electrons around carbon, and then write the structure for hydrogen, and then each of these 2 would be a bond between these 2 atoms. Or the same for like CCl4. You write the structure for, maybe I write it a little above. So CCl4. You write the structure for carbon, and then put like Lewis structure and put like 4 electrons around it, which are like valence electrons. And then you do the same for chlorine, and then you write 1, 2, 3, 4, 5, 6, 7. The valence of chlorine is 7, right? It's in group 7A. And you do the same here, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And I put like the ones that are single, the electrons, so I can form a bond between atoms. 1, 2, 3, 4, 5, 6, 7. And each of these form a bond between our atoms. So this is CCl4. And in an exam, I will ask you how many non-bonding electrons exist in CCl4. So you should count, these guys. So this is like 4 as for chlorine, right? Multiply by 1, 2, 3, 4, 5, 6. So it would be 24 non-bonding electrons. And if I ask you how many pairs do we have, you divide by 2. It would be 12 pairs of non-bonding electrons, because you count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Okay, the other thing that we talk about that is really important, is kind of like crucial, especially for like chapter 3, when we talk about Markovnikov's rule, is polarity. So, and then electronegativity. In general, if you have like 2 chlorine atoms, and then they form a bond, what you do, again, you put like 7 electrons around each of these, and they form a bond between them. So chlorine, because these atoms are the same, they attract electrons, the same way. The tendency of absorbing electrons is the same between 2 atoms that are the same, right? Because this is a fundamental characteristic of atoms. But if you have 2 atoms that are different, for instance, hydrogen and fluorine. Fluorine has a tendency to absorb or attract electrons more. We call this tendency electronegativity. And you have a table here, electronegativity table, that you should know that fluorine is the most electronegative atom, meaning that it has the most tendency among all elements to absorb or attract electrons. And something that I always tell students to remember is that more electronegative an element is, less metallic character it has. And if you look at the periodic table, I always use this table from like Chem 101, because you see like metals, non-metals, metallic. And any trend that you have in periodic table, specifically about things that we talk about in the class, if for instance, in group 8A or like 5A, metallic character increases from going above to down, it would be the same for all groups. So it's good to just like remember group, like for instance 5A or 6A, look at those, because you remember that you had like non-metals on top, nitrogen, phosphorus, and then you had like metalloids, and then you had metals like bismuth towards the end. So if you remember this, and then also horizontally as well, that you have like lithium, beryllium, for instance, group 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So bottom line is that in periodic table, when going left to right, metallic character decreases because you have metals, metalloids, non-metals, right? And the same thing, you can say when you're going up to down in one column, you have non-metals, metalloids, metals. So metallic character when you go up to down increases because first you didn't have metals, but now you have metals. So if you remember that, electropositivity, which is reverse of electronegativity, is the same as metallic character. So when you go left to right, since metallic character decreases, electropositivity decreases. And also up to down, metallic character increases, so electropositivity increases. So if you remember that, electronegativity is reverse. And also if you remember that fluorine is the most electronegative element, you know that, okay, oxygen is less electronegative, so basically electronegativity going from left to right increases because fluorine is the most electronegative one. And then also going up to down, electronegative, since fluorine is the most electronegative one, going up to down, electronegativity decreases. Okay, so if you have elements that they have different electronegativity, you will be having a polar covalent bond. So for instance, Cl2, it is non-polar because the bonding between chlorine and chlorine is, basically these two elements have the same electronegativity. Messing this up. Same electronegativity. So you have non-polar covalent bond. But for instance, if you have like HCl, these two elements have different electronegativity. So this would be a polar covalent bond. And then if I ask you the definition in exam, a polar covalent bond is a covalent bond in which the electron pair is not shared equally between the two atoms. As we said, one electron likes to absorb it more, right? So remember that polar, so because students tend to see, for instance, a non-polar, this is what I do in exam, I say, is the following statement true or false? A non-polar covalent bond is a covalent bond in which the electron pair is not shared. And then since the students hear non-polar, not shared, they think the statement is correct. But if you remember what polar covalent bond means that we have different electronegativity. It means that one atom, for instance, in this case, chlorine, absorbs electron more, right? So the electrons are not shared equally between the atoms.
Is the only way you can have a non-polar bond to have the same element twice?
Yes. So we have, actually, this is a great question. So one thing that we have is like polar bond. The other thing is like polar or non-polar molecule. And this is the thing that we covered in chapter 2, I believe, that we have like some molecules like, for instance, CH4, all are alkanes, that their bonds, for instance, for CH4, as we just draw the structure here, each of these bonds are non-polar, but the molecule as a whole, or sorry, I did that reverse. Each of the bonds, since carbon and hydrogen, their electronegativity is different. So your book says that we consider them being really similar, but in general, if you look at the numbers, they are different. And then you have like some molecules that, for instance, CO2 is a good example, that each of these atoms, the electronegativity is different. So these bonds are polar, but because of the arrangement of the structure of the molecule, this molecule as a whole is non-polar. Okay, but when we're just talking about bonds, as long as you have different elements, the bond would be non-polar. But as I said, your book for like carbon and hydrogen, consider the electronegativity of these elements to be really similar. Really, that is embarrassing. I know how it is. Really, really similar. Okay, so that's why all your alkanes are non-polar. Okay, and then we talk about this more when I go through chapter 2. But as of right now,
all the alkenes are nonpolar?
all the alkanes.
Alkanes. Sorry.
Alkanes,
Okay.
yeah. Double bonds are different, and I didn't talk about for like alkenes and alkynes. This is different story, but we didn't cover those in the class. But for alkanes, remember that the bond is or like the molecules are non-polar. Okay, and let me just like give you examples of like writing Lewis structure. For instance, for CO2, 1, 2, 3, 4. You put 4 electrons around it, right? Because the valence is 4. For oxygen, the valence is 6. So you put 1, 2, 3, 4, 5, 6. And then I want to write CO2. And then the same thing for the other oxygen. 1, 2, 3, 4, 5, 6. And how you do this, and then I always try, so 1 electron here with this electron here, and the other, these two, they share electrons, and also the other two. So this is structure. So this is to demonstrate why this is happening. But as you see, this structure is kind of ugly. So how we write it is like this. So that's why CO2 has, each bond between carbon and hydrogen are double bonds, and this is how you technically write this structure. So we should know these things to kind of like understand how we write the structures and all that, but this is not the focus of our course. This is kind of like the language, kind of like knowing alphabet to know how to write words. We focus on writing words kind of, but not knowing, I don't ask you specifically, these things to write the structures for this class, but you should know. So when we talk about double bonds, single bonds, you have an idea. And a double bond, as you see, we have like 4 electrons shared between 2 atoms. And if we have triple bond, we have like each dash has like 2 electrons. It would be 6 electrons being shared between the atoms. And also these guys, we call them non-bonding electrons. So these are valence electrons that they don't participate in bonding. And we have also some definitions that I'm just going to read. I'm not going to write, but I just write them here to be faster. So hydrocarbons, what is valence? So hydrocarbons are compounds composed of just hydrogen and carbon atoms that we talk about them a lot, like CH4, C2H6, C2H2, all that. And the valence of an element is the number of bonds that an atom of the element can form. And this is the main element that we're interested in because we're studying carbon compounds. So this number of bonds would be would be 8 minus number of valence electrons. Because as I said briefly, if you have like nucleus and then we have like first shell, second shell, all the atoms, they want to form bonds or lose electrons, gain electrons, so that they have like reach an octet. They have like 8 electrons in their valence shell, except hydrogen, helium, and then lithium, and also beryllium. They want beryllium loses 2 electrons, so they reach and do it because they don't have more electrons to lose or gain. Does that make sense? So these are like definitions that you should know. What are hydrocarbons, what is valence. So the number of bonds that an element can form, we call that valence. So that's why we say valence of carbon is 4. And this is why I write structures like this, and I ask you guys, I say, okay, how many hydrogens should be here? You count 1, 2, so 2 is left, so this one should be 2. What about this one? Right, this carbon, you say 1, 2, 3 bonds, so 1 is left, so 1 hydrogen, right? Or like here for this carbon, again, you say 2 bonds are already taken, so 2 more bonds. So this is basically equivalent, maybe this is not the best choice of color. This is equivalent to writing like this, that you have 2 bonds here, 2 more of hydrogen, or like 3 here, 1 hydrogen here, 2 bonds here, 2 hydrogens here, 2 here, and then 3 here. So this is the whole reason, again, I had to explain the things that I just explained, so you know why we're doing what we're doing. Okay, so if I give you, for instance, this structure, right? So you assume that, or I assume that you know how many hydrogens exist in this structure, because you count here, this carbon has 1 bond, so it should have 4 bonds, so we should have like 3 hydrogens here. And then for the other carbon, we count number of bonds, 1, 2, 3, 4, and each of these lines or like dashes we call a bond, right? So here we have 4 bonds, so we cannot have more bonds because the maximum is 4. That's why we don't write any other hydrogen. Or like here for the other carbon, we have like 1, 2, 3, we need 1 more bond. So we put like 1 hydrogen here. So this we call, CH3, CH3CCH. This is abbreviated structural formula, so give us information how we bond atoms together. But if we want to see the whole story, it should be like this. This is expanded structural formula, that you see how atoms bond together. And even if you put this hydrogen here, not here, that is correct. So as long as you know that you should have another bond here with hydrogen, you're fine. Okay, the other thing that we talked about in chapter 1, and we're going to talk in more detail in chapter 2, is isomers. And we have different types of isomers. The type that we talked about in chapter 1 is a structural or constitutional isomers. And these are molecules that they have the same chemical formula, but different structural formulas. Meaning that, for instance, if you look at like these two, ethanol and methoxymethane, like CCOH, H, and HCOC, H. So if you write, and then I ask you in exam to write the chemical formulas of these. So you count the number of carbons here is 2, right? If I can't write correctly, C2. And then how many hydrogens? 1, 2, 3, 4, 5, 6. And then 1 oxygen. And then if I do the same below, you have 2 carbons, 1, 2, 3, 4, 5, 6 hydrogen, and 1 oxygen. So chemical formulas are the same, but the arrangement of atoms, here you have carbon attached to carbon and then attached to oxygen. But here you have carbon attached to oxygen attached to carbon. So here you have like oxygen in the middle, here you have carbon in the middle. So the structural formula, so the structures are different. So these are, we call them structural or constitutional isomers. So, and then in the next chapter we talk about different types of isomers.
Do polar and non-polar molecules have like? Would this be non-polar and this one be polar because of the way they're arranged? Because this is like equivalent on both sides and this one's not, or does that not affect things outside of hydrocarbons?
That is a great question, and I think in theory the arrangement of atoms can change polarity and non-polarity. In this case, because we have like this oxygen which is like much more polar or like much more electronegative than the other two atoms, actually that's a great question. So it can change polarity. I'm not quite certain, so this one I think ethanol is polar for sure, and this one I guess I should check, but as you said, this is kind of like symmetrical. It's kind of it can be like CO2. So when we have like different contributing factors, we should consider arrangement of atoms and also different bonds. So I should check on this. I don't know off the top of my head if this molecule as a whole is polar or non-polar. But for your exam, I'm just going to ask about whatever I talked in the class.
Okay.
So you don't have to worry about it. So your alkanes and CO2 are the ones that are non-polar.
So it'll just be basic hydrocarbons or CO2.
Exactly.
Okay.
So anything that we talked about in the class, I'm going to ask about that.
Okay.
But that is a great point. Okay. So, and then we had like a definition here, I think. Let me see. Okay. So that's like catenation I'm looking for. I think it was like, here. So the other definition that we talked about in the class is catenation. That is the ability of atoms of the same element, of an element. So let me read it. It's the ability of an element to form chains of its own atoms through covalent bonding. And then this is something that we talk about in this class. So we have like these carbon chains. We call that catenation. And this is something that I was asking in your exams. And let me see if we have more definitions. And then the molecular formula of a substance gives the number of different atoms present. The structural formula indicates how these atoms are arranged or like bonded together.
Do carbocations have anything to do like with the catenation? Like are those two, because the words are, in English they're similar, are they linked or not?
Yeah, I mean, that's a great question. So carbocations are like carbons that now have a charge. But right? Do you remember that when we talked about like, for instance, we had like, here is R. We had like tertiary carbocations that we have like, 1, 2, 3. So it should be, So it's like a carbon that has positive charge that is attached to 3 different groups. Or when we had like, secondary, we had like 2 groups, that this is attached to, and 1 hydrogen. And then let me bring the corresponding thing too. I have like the structure, similar to what you wrote, which is here, I believe. Okay, so this is pretty similar. So this was tertiary. So carbocations is a carbon that has positive charge. And if this is tertiary, it means that it's attached.
So the cat comes from it being a cation, not from the catenation.
Exactly.
Okay,
so those are like different.
Okay.
But now that we're talking about this, I can just like cover these two. So this is secondary. So this is basically a carbon that has positive charge that is attached to 2 groups rather than hydrogen. And it has 1 hydrogen. And remember, the valence of carbon was 4. So theoretically, it should have had 4 bonds. But since it has positive charge, it's lost an electron. So it's not sharing anymore with that. So the valence would be now 3. As like 1, 2, 3 bonds. Does that make sense? And then for this one, secondary, it attaches to 2 different groups and 1 hydrogen. And then this denotes a positive charge. That's why we have 3 bonds. And then primary is when this carbon, which has positive charge, attaches only to one. So that's why it's just primary. To one other group
Is there two hydrogens on it?
Exactly.
Okay.
So 2 bonds, and then 1 here would be 3 overall. And then finally we have methyl, or like unique, that it has like attached to 3 hydrogens. No other group, just like no R, just like 3 hydrogen. So this is methyl or unique. So we call these carbocations. So the name is similar to catenation, but these are completely different.
Yeah, I was getting like cations and like catenation. Like I was getting those two coming from different areas. So so methyl is, so you get methyl from losing an electron from methane, right? So and that's the same for like propyl or anything. So is that what's that called when it loses? Because I know it changes the name of it because it has the YL suffix, but what is that called? Like where it loses that electron? I get. Am I not asking that right? So like what process takes it from methane to methyl?
Okay. So what is the name of the process you're asking?
Yeah, so or if you can even just explain the process. Like I want to know how do you get from methane to methyl? Like I understand that that's methyl because it lost an electron. But why did it lose an electron?
So it depends on what type of reaction we're dealing with, and depending on what type of reaction we have, it can be different processes that we can, have methyl. For instance, that's a great question. One thing that you had in chapter 1, one example, is that, for instance, if you have actually ethane, which is C2H6, right? If you see the structure, and then if you want to write it, so now we know that we just write it like this, right? It's kind of like, that you have like 2 carbons, and then you fill it with hydrogens, and the valence of carbon should be 4 in each of these. But even if you write the Lewis structure, you can 1, 2, 3, 4, the other one 1, 2, 3, 4, and then 6 hydrogens all around. Each of them has like 1 electron, right? And then these 2 electrons, you form a bond between them, right? So now if you give like ethane heat, right, so you break down this molecule, so it would be 2 methyl radicals. So this would be, for instance, one example. The other example is in your chapter 2, when we talked about like the chlorination process. Bromination, chlorination, kind of like hydrogenation in general.
Is heat the only thing that would break up, that would like cause that reaction? Or is it usually what would cause those to separate into the 2 methyl groups?
Yes, so because these are really unstable, usually you should consume, like it costs you something to do that. So one thing would be to give them energy to make them to separate, because these guys are really unstable. So you should like spend whether like heat or like work to do that. But one way would be heat, And the other thing that we had in chapter 2 that I'm trying to find, when we had like reaction mechanism, wasn't it here? Or maybe it was chapter, I think it was chapter. Okay, here. Here, for instance, in like chlorination or like halogenation in general, when we had like the chain propagation step, we had like our alkane plus chlorine atom, right, that would give us alkyl radical plus HCl. So this is another way that we can produce. I'm going to talk about this in more detail, but just to answer your question, there are like several ways that we can produce these methyl radicals, or like in general alkyls. But yeah, we just talked about this in the class. Okay. So now let me go to here. Okay, and then we talked about isomers. Okay, so I'll hold on to formal charge because that is not directly related to what I'm talking about. And then I'm going to, before your final exam, I'm going to tell you what I'm not going to ask in the exam, final exam. So this arrow formalism, I'm not going to ask you in your final because as long as you know the concepts. I mean, that is not so crucial for the purpose of our course. But one thing that was in your exam 2 and quiz 3, and I'm kind of like reviewed, I went back to chapter 1 to view them, is like sigma and pi bonds. So this is sigma, this is pi. So when we have like the electron configuration, when we have atoms, we have like, atomic orbitals. That they were like S, P, D. Remember, we were writing 1s2, 2s2, 2p6, and so on. So these are atomic orbitals. But when atoms form bond together to form molecules, we have now molecular orbitals. And molecular orbitals can become so complicated, and it just needs like lots of practice and all that. So what I'm asking you in the exam would be just among what I taught you in the class, so you don't have to worry about it. And one thing is to distinguish which one is pi, which one is sigma bonds, or like which orbital you have. So in general, there's only one instance that you have a pi bond, when you have lateral overlap between two p atomic orbitals. And now I'm going to just do this because I had difficulty to writing this kind of p atomic orbitals. So if these two guys combine, you see, you will be having kind of like,
This is the pi bond,
exactly,
and you said this is the only way it forms?
yes. So this is how your book writes that, kind of like this, and I apologize for the distortion, but it's kind of like this. So this would be pi bond, and then how I write it if I draw the structure myself would be something like this. As you see, this is lateral overlap, so you have like this lobe here kind of like overlaps with this lobe, and then this one here overlaps with this one. So this is pi bond. This is the only instance that we have pi bond and we are studying in this class. Anything else would be sigma. And then sigma would be the end-on overlap, meaning that if you have like, again, this p atomic orbital, right, and then you have another one like this, you see that you have like their ends overlapping. And then if you have like the axis for these two, it matches, they are the same. But the axis for these two, they are kind of parallel, they're not the same. So you should have the same axis when you have sigma. So as I said, this is pi, anything else is sigma. And then you just see that in these two formats, or like these two mixing together. Anything else, for instance, if you have like a s orbital and kind of p orbital, again, if you draw the axis, they match. It's like end-on overlap. Or sometimes you have like hybridized orbital, like sp2 or sp3, and then you have like a p orbital, which is like kind of like this. As I say, I apologize for the drawing, but this is like p, this is like hybridized, for instance, sp3. So again, if you have the axis, they match. So all of other ones, or like if you have two s, these are again, sigma. All of these are sigma, and you have like examples in your book, sigma bond. So this is ps, this is pp, this is sp3s, this is sp3 all of them. If you draw the axes, they match, or they're like end-on overlap. The only one that is lateral is pi. Okay, so this is one thing that we talked about like sigma and pi bonds. The other thing is that, okay, how do we get sp3 or like sp2? So if you write energy diagram, and then if you have like, for instance, for carbon, right? Carbon has 6 electrons total. And remember that first we fill 1s and we put 2 electrons, and then 2s, 2 electrons. So we have 4 total. Each of these arrows are like 1 electron, right? And then we have like 2p that has like 3 orbitals. This, right? P has like px, py, pz. So we already put 1, 2, 3, 4. So 2 electrons are left. So one would be here, the other one would be here. So we have overall 1, 2, 3, 4, 5, 6. And we had Hahn's rule that each of these, orbitals, when they have similar energy, we fill them singly first and then pair them up. So you don't need to go into much detail. Just know, for the purpose of our class, this is atomic electron configuration for carbon, right? And then 1s has the lowest energy, and then 2s, and then 2p has like higher energy. Okay, and when we, when, for instance, carbon wants to, form bonds with like 4 other hydrogen, what happens is that so we don't deal with like the 1s, because this is not our valence electrons. When we want to form bonds, we work with valence electrons, right? Not with outermost shell. We just write that in the kernel, and then we put 4 electrons around carbon, because these guys are forming bonds. So we're only concerned with valence electrons. So we have 4 electrons here. What happens is that 1 electron here goes to this empty orbital here, and all of them would form similar energy, which is between S and P, right? This is only what makes sense, because these, the energy level, because these guys kind of like the electrons are mixing together, the electron cloud, so the energy would be between S and P. It wouldn't be higher or lower. That's why we put these 4 energy level between S and P, because 1 electron here goes here, and then the energy of each of these would be between S and P. That's why in your book, when you see like sp3, first of all, you have like 1, 2, 3, 4 overall, and their energies are the same, and this energy would be between S and P. Does that make sense?
No.
So why not? So I guess this is like theoretically what happens.
Mm-hmm.
So when we want to go from like atomic orbitals.
So I guess where I'm lost at is I understand that we're like dealing with orbitals, that this is molecular orbitals?
Yes. So these sp3, yes.
Okay, so what is the difference between, okay, so I remember the atomic orbitals.
Uh-huh.
That makes sense to me. I don't understand the difference between the atomic orbitals and the molecular orbitals.
Okay. So the difference is that we want to see in molecular level, in like atomic level rather, what happens when we have like 4 bonds between, these carbon and these hydrogens. We want to see how going from atomic orbitals to molecular orbitals. So those sigma and pi bonds that we talked about, we want to see exactly what happens here in an atomic level. Does that make sense? So transition from atoms to molecules.
Okay.
So theoretically, this is how chemists or like physicists explain, having methane, for instance, that we have like 1 electron in 2s of carbon going to 2p, and now we have like 3 sp3 orbitals. And then if you look at your book, you know, yeah.
So my next question is, so I remember this, so that the first orbital is 1s2, the next is 2s2, and there's 2p6. So why are there only, where are you getting the 3 lines here and the 4 lines here? Like, why is there not, because there's 5 total, or you know, or it's, you know, where's the 2p6? Like, I guess I don't understand where are your 3.
Okay, so this comes from number of electrons in carbon. Carbon maximum has 6 electrons. So 2 of them are like in like field shelled electrons that we're not dealing with it. And we have like 4 more.
Okay.
So in atomic we have like 1, 2, 3, 4. But when we want to transition to molecular orbitals, one of these electrons here, let me have it with like this one. This electron comes to pz basically, and then all of this would be having the same energy. So that's why we don't have more electrons, because carbon doesn't have more electrons. Okay.
So when the electron goes from the 2s to the 2p, what does that mean? Like, why is it going there, and what does that mean for, like, how do we know how many electrons are, like, how are you getting from this electron moving to sp3?
Okay, because then first of all, how it happens is like whenever you have like single bonds, you have sigma bonds. So for these specific, you know, this is like another subject. As I said, molecular orbitals, how we do what we have is based on what scientists came up, and it's just another subject, you know, that people study. So we're not going to specifically talk about that. But for each molecule, electrons hybridize differently. So this is the case for methane that we're studying here, that we have like 4 sp3 orbitals. And the reason that we call that sp3 is that we have, you know, 1 electron left after this electron here. Let me have another color. So when this electron from S leaves the 2s and goes to 2p, now we have 1 electron basically in 2s left, right? Do you know what that
so
means?
yeah, so and then when it went from 2s to 2p, was that empty? Was that like electron slot empty to start with? So 2p only starts with 2. The 2p only starts with these 2 electrons, and then the 2s moves and gives it a third one?
Exactly.
Okay.
And now we have this color. We have like, you know, 3 in P, 1 in S, that as we said, when you have molecular orbital,
I got it.
all of them now have the same energy. The reason that we call that sp3 is that, so now we have 4 sp3 orbitals. And the reason we call that sp3 is that there is 1 share of S, 3 shares of P. And then when you see the, you know, molecular structure, and I'm showing like the methane structure, I mean in my book it's like page 25, and it's like in section 115 in your book for people who, if they watch. So now you have like 4 sp3 orbitals that they form bond with like s orbital of hydrogen, and now this is how you get methane molecule.
Got it.
Does that make sense?
Yeah.
So this is kind of like more theory behind it, but as I said, I just asked you this much in the exam, nothing super complicated. And you should know that when you have single bonds, you have sigma bonds, and then if you have like double bond, one of them is sigma, the other one is a pi bond. Sigma, the other one pi. And this is what I was asking in the homework. That I think I asked for ethene. How many sigma and pi bonds you have in total? And sometimes the students forget to count these ones too. So these are single bonds too. These are sigma. So 1, 2, 3, 4, 5 sigma, and one pi bond. But again, as I said, what I'm asking you in the exam would be just similar. And the reason, oh, I'm going to, when I go to next chapter, I'm going to talk about also sp2 hybridized. But here you have like sp2 and kind of like sp2 and s orbital, that again it would be sigma. Okay, but as long as you know single bonds are sigma, you can answer the question that I'm asking you in the exam. Does that make sense?
Yep.
Okay, so that was chapter 1. Okay, now let me go to chapter 2. So what you need to know is that we have alkanes, and I'm going to talk about chapter 3 too. It's kind of like similar concepts. So we have alkanes, alkenes, alkynes. So you should remember that alkanes have the general formula of CnH2n plus 2. Okay. Alkenes have the formula of CHN 2n, and then alkynes have the general formula of CnH2n minus 2. Okay, and we have like you have like your table 2.1, and everything that most of the thing, I highly encourage everyone to read the book, and I kind of mandated that, I guess. I couldn't enforce it, so most of the students won't have the book. But I even had students that they came to my office, and then after I told them to read the book, and now they're like, yeah, you were right, having the book is really beneficial. So, but I have these things in your PowerPoint slides too, so you can refer, and I think when I posted each lecture, I said what chapter I'm covering, so it would be easier to navigate. Anyway, so you should remember that methane has 1 carbon, so number of carbons. Ethane has 2 carbons. Propane has 3. Butane has 4. Pentane has 5. Hexane 6. Heptane 7. Octane. It becomes messier and messier as I get to the bottom of this page. And then nonane is 9. Decane is 10. And some of these are easier to remember. So decane is decade is 10. Nonane, if you heard of nanotechnology, is 10 to the power of minus 9. So they have the same root. Octane, as your friend said, octopus is 8 legs. So it's kind of coming from the same root. And then hexagon or hexagonal is 6, or pentane, pentagon, or butane is 4. Now I'm just like repeating what is written. So just remember, especially methane, ethane, propane, butane, pentane, hexane, heptane too. You should just like remember this, okay? And then if you want to write an alkane, you should remember CnH2n plus 2. For instance, if you want to write methane, so for instance, methane, CnH2n plus 2. Methane would be C1H, 4. You substitute 1 here, so it would be 2 plus 2. Or like ethane would be C2H6, then C3H8, and so on. You can, as a practice, write for all of them. And then when you want to write the structure, so the fundamental is what I just talked about, to write Lewis structure for all elements, for like carbon, hydrogen. But when you just practice, you realize that for methane, you just put carbon and then attach 4 hydrogens, okay? Or for like ethane, you have like 2 carbons and then attach the rest hydrogen, and then you have only single bonds in alkanes, okay? Or like if you want to write decane, you write 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you feel, you should know that valence of carbon is 4. So you put like, 3 hydrogens here, 2 here. And the reason we don't put more is that 2 is already taken. The valence is 4, right? And then we put hydrogens all around. I didn't do a good job writing this. So now, something that I asked you in the exam, and it's a big topic of what we're studying, is like IUPAC naming. And as we said, IUPAC, where did it write it? It's like International Universal, where was it? Nomenclature. Okay, IUPAC. International Union of Pure and Applied Chemistry. So this is basically what we focus in this class, so how to name compounds. So what you do, first of all, you should know the root name of an alkane is that of the longest continuous chain of the carbon atoms. So if I give you a compound and then say name it, for instance, let me 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and then we have like 2 CH3 attached here. And as we said, sometimes we just like, instead of writing all the hydrogens, I just put 1 here, 2 here, and 3 here. Okay, so the first step in naming an alkane is to find the longest chain, and it gets kind of tricky sometimes because we talk about some examples that maybe you have a branch and that branch would be the longest, so you should go through it. But in general, you find the main chain that has the most number of hydrogens, right? So for instance, here, 1, 2, 3, 4, 5. But if I go, for instance, the other directions, for instance, if I say 1, 2, 3, this is only 3. Or like here would be 1, 2, 3, 4. Right, so this would be the longest chain. And then the next thing that we do, we find substituents. That substituents are groups attached to the main chain of a molecule. So here we have like 2 substituents. And if you have, basically, if you drop 1 hydrogen from alkane, if you eliminate 1 hydrogen atom, you get an alkyl. For instance, if you have methane, which is an alkane, and then you eliminate 1 hydrogen, you get CH3, that is methyl. Okay, or like ethane, if you eliminate 1 hydrogen, would be C2H5, this is ethyl. Or like propyl butyl. Okay, so first you find the main chain, and then you find the substituents. And what we do is that we name the number of, and then when you have substituents, you should name the chain somehow that you encounter the substituent first. So if we go left to right, we encounter that the second carbon, but if I go right to left, it would be 1, 2, 3. So since here I encountered that sooner, I go left to right. Does that make sense? And then if you have like more substituents, right? It's kind of like the example that your book gave. For instance, where was it? Okay, so if you can go left to right or right, here if I go left to right, I have 1, 2. If I go this direction, also I get 1, 2. We go from the direction that we have kind of more branch, or like we reach the 3rd branch sooner. And if everything is like the same in our structure, we go alphabetically. Okay, but in either case, when you want to write the name of the compound, you write it alphabetically. For instance, if you have like, the other thing that I should mention is that if you have chlorine as your substituent, or like bromine, or like halogens in general, you call that chloro. You call this bromo. Or like F, you call that fluoro. Okay, and then the other substituents that you can have, it can be methyl, it can be ethyl, right? Methyl can be ethyl, and so on. So now let's just practice some. For instance, I'm just going to write the carbons, right? Because you can just fill out the hydrogens yourself. Okay, so now in this case, first of all, the longest chain is just like this one. This is kind of straightforward. And then if you want to go left to right or right to left, again, both of them you encounter the branch. These are your branches, right? On second carbon, but we go left to right because you have another branch right after here. So we say 1, 2, 3, 4, 5, 6, 7, and we call this compound 2, 3, 6. Okay, and you have methyl groups, but how many do you have? We have 3, right? We have 3 methyl groups. So first we write the name of the number of carbons that the substituents are attached to, and then we have 3 methyls, and then the way that to write 3 is tri. It's kind of like di means 2, tri means 3, tetra means 4, and this is all you encounter in this class. If you encounter more, I tell you, but knowing that di means 2, tri means 3, tetra means 4, so you have 3 methyl. Okay, and you have 7 carbons on your main chain, so you write the name of this compound as heptane. So the number of carbons in main chain denote the name of your compound, and if you only have single bonds on main chain, it would be alkane. So this is an heptane. Okay, and then this is like the number of substituents that you have. So in this case, since we have like 3 methyls, we call it trimethyl, and this is like the number of carbons, or that the substituents are attached. Okay, so I'm going to skip the rest of the materials for now because these were like in your exam 1. So hopefully, I may record another video, or like in some tutoring session, I talk about them. But since from now on, sigma and pi bonds was in your exam 2 too, or like your quiz 3. But I wanted you to know, because if you didn't know how to write Lewis structure, or like what is valence, or what is catenation, all the other chapters don't make sense. But the other ones, like kind of like solubility or like intermolecular forces, those guys we can just like skip them. It's not like crucial for the rest of what I'm talking about. Okay, so one thing that I asked you in the exam, and I'm going to ask you in like makeup exam, is reactions. So you should know in general that in alkanes we have substitution reactions. Okay, and now that we're talking about substitution, know that in aromatic compounds, which are compounds that they have a benzene ring, benzene, if I spell it, benzene ring, they have like a benzene ring, we also have substitution. And when I go to chapter 4, I talk about more why that is. But in your alkenes, let's write that here, alkenes, we have addition reaction. And I always ask you true or false. Is the following statement true or false? Aromatic compounds, or like benzene, reacts by addition. So benzene is substitution, is like alkanes. And then alkanes are also, as I said, substitution. So the only one that is addition is alkenes. So lots of my exam, because there are like multiple choice questions, lots of it is just like paying attention to the question. Sometimes the students know the answer, they come to my office hour to go through the questions, and then they say, oh, I chose this answer because I thought you said which one of the following is correct. And then I had like not capitalized. So make sure to read the question well. And in general, now let's talk about substitution reactions in alkanes. You can write alkanes and RH, because as we said, if you remove one hydrogen from an alkane, we have alkyl, right? So by the same token, if I add an hydrogen to alkyl, would be this one as overall would be alkane. So in general, RH plus, you know, a halogen, and as you know, maybe remember from like your chemistry class, halogens, they exist as diatomic molecules. So for instance, we write Cl2 like this. So if we give these molecules heat or light, okay, what happens is that we have substitution, meaning that one of these chlorine and this hydrogen, they switch places. Okay, so we'll be having R Cl plus HCl. And this is what I asked you in exam. I say how many, for instance, monochlorination products is possible in a specific compound. And, you know, I asked you, you know, how many organic compounds. So this compound here, since it doesn't have hydrogen, this is inorganic. But this guy here, because it has like carbon and hydrogen, this is an organic compound. And let's talk about a practical example. For instance,
Is that radical always going to be a methyl group?
methyl, ethyl, propyl, depending on what you have. Yeah, so
Okay,
this is
but it'll be
alkyl.
stated at some point what that radical group is.
Yes, so for instance, in your exam, I gave you a structure, and then I said, how many monobromination products is possible from reaction of cyclopentane with bromine molecule? Does that make sense? So I give you the compound,
Yeah.
you know, unless I just give you the general reaction and ask, you know, which of the following is correct or incorrect. Does that make sense? But in general, I give you the compound so you can answer the question, okay? So, for instance, if you have methane, so methane is CH4, right? If you say CH4 plus, you know, Cl2, you switch this Cl and this hydrogen. So the product, and then here we write light or heat, it would be like CH3 Cl plus HCl. So what we did, we just switched these two atoms. Okay. And okay, one thing that I asked you in the exam, and I'm going to keep asking you, is that when we have enough chlorine molecule or like bromine molecule, depending on bromination, so the reaction of alkane with bromine molecule, we call that bromination reaction. Or like in this general, you know, if you have like alkane plus halogen, this reaction we call halogenation reaction. Okay, so if you have like this halogen is chlorine molecule, it would be chlorination. If this halogen is like bromine molecule, it would be bromination. So when we have enough chlorine molecule, your product, again, this CH3Cl, again can react with this chlorine molecule. So what happens now is that another hydrogen...
Is this the complete chlorination?
Exactly. So when I say complete, you continue this process until all these hydrogen atoms substitute with chlorine. So this one would be...
So it would be a carbon surrounded by chlorine.
Exactly. So
okay.
this one would be...
That makes sense now.
Okay, it would be like this. So these two we switch places, right? Plus HCl. Okay. And then if we do that again, and then you should have light or heat. If you do that again, CCl, HCl plus Cl2, again with heat. I wrote that in the atomic bond. I meant to write it here, heat or light. And then again, heat or light, you substitute this hydrogen with this chlorine, and then write the same. So it would be like Cl, CCl, hydrogen, Cl plus HCl. And then here again, if you have enough chlorine, you can do that one more plus Cl2, one more time, Cl2. And then you substitute this hydrogen with this chlorine. So you have Cl4 plus HCl. So if I give you this in the exam, I say what is the product of, if you have enough chlorine, or if I say what is the product of halogenation or like chlorination of methane, if you have enough chlorine, or what is the product of complete chlorination of methane, right? So what you do basically, you substitute all hydrogens with chlorine, so it would be CCl4, okay? So that is kind of like the shortcut in a sense. So instead of writing all these steps, you know that in each step you have one hydrogen substituted with chlorine. So when you have like the complete chlorination, you substitute all the hydrogen atoms with chlorine. Okay, and this is similar. I think in your exam I asked for butane, so it's like C4H10. So the product of complete chlorination or like bromination of that, whichever I asked, it will be C4Cl10. So you just substitute this hydrogen with like chlorine.
So does the language matter in the questions? Like, if you ask for the chlorination versus the complete chlorination, would the chlorination just be the first step,
yes,
and the complete chlorination be all the steps?
Yes,
okay.
And I'll be specific. I'll design the question somehow it won't be confusing. And if anytime I do a mistake in the exam or something is confusing, I just eliminate the question, like what I did for exam 2. So you don't have to worry about it. Okay. So something asked in the exam is that, for instance, here we have like cyclopentane, right? Cyclopentane. And how we name it is that we have like 5 carbons in the ring, so we call that pentane, and all are single bonds, so it would be A and E. And it has a ring, so it's cyclo, right? And we don't have any substituent, so we don't have to denote any numbers or anything. And I'm going to, so even if you have one substituent, we don't put any number, because for instance, when you have this structure, even if you have one Br attached here, if I don't have to name it, one bromocyclopentane, because even if I put it here, when I kind of like rotate my iPad, you see the same structure, So that's why anytime that you only can have one possibility, you don't write any number, because you don't need to. Okay, so now if we do the same here, plus Br2, we're doing halogenation, and then here we put light or heat. So when you do that, again, this is kind of like similar. I always write the hydrogens for myself, so I know, here we have 2 bonds, we have 2 here, we have 2 here, 2 here, 2 here, 2 here, and then Br2 is like this. As we said, remember, you have alkane, so it would be substitution. And as I said, this is easy, but in exams you get confused. I guess like pentene, you don't pay attention, So as long as this is substitution, you should have 2 products. But sometimes, okay, now when we have like this structure cyclopentane, I say the equation that you see on exam would be how many monobromination products or how many organic compounds is possible when we have monobromination of cyclopentane. And you should remember, first of all, when we have alkane, we have substitution reaction. So this is one thing. The other thing is that in substitution, we have one of the bromine being substituted with one of the hydrogens here, right? And then if I have like the expanded structural formula, we have like this carbon attached to two hydrogens, right? CH2. So what happens, we switch these two guys, right? So to write that here, kind of like write it like a house, you know? So when we were a kid, this was our drawing. This is like a window or whatever. Anyway, so this is like easier to draw than like pi orbitals. Anyway, so we have like this carbon that is attached to one Br, one hydrogen, plus HBr. And this, you know, here, it doesn't matter which hydrogen we substitute. Even if we substitute one Br here, and then it has one hydrogen, again, would be the same structure, you know. So that's why this is only one product possible when we have monobromination of cyclopentane, right? Because even if you substitute, you know, so this is like CH2, right? Right, this is kind of like, so even if you substitute this Br with this hydrogen, and then we write the structure here, it would be one Br and then hydrogen. So if you again rotate the iPad, you get the same structure, okay? And that's why there is only one product possible. But if we have, for instance, let me see another example.
So in this, with your, so you got your cyclopentane and your bromine, bromine molecule. If you were to take both of those bromines and put both of them onto the cyclopentane, would that be the complete bromination or the dibromination, or what would you? What
That would be
dibromination.
dibromination. Yes.
And so then it would just be, you'd have your dibromocyclopentane plus 2H or H2.
Yes, basically, yes. So you get this structure, basically the same thing that we did before. You get this structure, right? And then you react that with another Br2. And then depending on, so in this case,
then you'd end up with 2 HBr.
So now, so this is Br2, right? Again, you have substitution reaction. So one of these guys, you know, can substitute this, or in this case, it matters which hydrogen we substitute, and depending on which we substitute, it would be different configurations. For instance, if you substitute it with this one, you will be having like Br plus, so this one still would be HBr, right? Because these two guys switch places.
But do you retain your HBr from the first one? So would this be 2 HBr? Because you've done bromination twice?
So now you don't have 2 HBr.
Okay.
Right? Because you're just substituting these two with each other, right? Does that make sense? So these are like different reactions. It's kind of like the reaction that we had here for complete chlorination of methane, right? So you don't write 2 HCl now. It's just like one.
Yeah.
Okay? But now here, it matters that which hydrogen, this hydrogen won't be the same as substituting with this hydrogen, right? So if you do that, I mean, your friend the other time said when I double tab, it changes to eraser, but sometimes I'm just like talking, I don't tap on anything. But anyway, I should go, talk with her about that. Every student helps me with something, one student helps me with QR code, the other with iPad, anything. So if I substitute this hydrogen with this Br, it would be like Br, and then while we have still this Br and this H, so this would be different from this one. So this question would be and then it would be like more structures as well, and it would be like how many dibromination products is possible, but I'm not going to ask you dibromination because it would be like more possibilities. It's mostly like kind of like a math question in a sense. If you talk about the statistics and all that, you don't have to worry about dibromination products, and you have examples in your book. But here you don't have to worry about
dibromination?
Yes.
Okay. So just for my understanding of this would be written as dibromocyclopentane
Uh-huh.
because there's only one configuration possible, right?
Yes, and I believe I think here you should specify the number of carbon.
Do you need to specify the number? Because if those two bromines were over here, it'd be the same thing.
Because here it also would be dibromocyclopentane,
But wouldn't
right?
it be like 1, 2?
Exactly.
Dibromo?
But here it would be 1 and 1. Right.
You would write 1 and 1, or would it just be because there's only like you said up here, if there's only one product, would it only be?
So if you write dibromocyclopentane, it can be 1 and 1, it can be 1 and 2, it can be 1 and 3, right?
Yeah.
So I think in this case you should specify 1 and 1.
Okay.
Because again, you don't have only one. If you say dibromocyclopentane, it means that you have 2 bromine in your structure. So I think you should specify 1 and 1 here. Okay, great question. So, and then we have like some definitions here. One of them is reaction mechanism. So reaction mechanism is a step-by-step description of the bond breaking and bond making processes that occur when reagents react to form products. For instance, here I told you this is halogenation reaction. We have chlorination, we have bromination. But I didn't tell you exactly how the bonds break, how the bonds form. So for instance, the free radical chain mechanism of halogenation, this is one example of reaction mechanism. Okay, so this is reaction mechanism that is a step-by-step processes that tell you how bonds are being broken, how the bonds of products are being formed. Okay, and for the case of halogenation reaction, we have 3 different steps. One of them is initiation, the other is propagation, the other is termination. And you should know these for your exam. Probably it was better if we would space them out. Propagation and termination. So the general reaction, you know that you have an alkane that reacts with Cl2, Br2, a halogen and produces HCl or HBr, and your what do you call it? Alkane halide. Let me see. What was it? For instance, depending on what the structure if you have. Like you have your alkane that one of the hydrogen is substituted with a halogen. Okay. So the first step is initiation. Basically, we have like Cl2 molecule that, if we give it light or heat, the bond between the chlorine molecule will be broken. So we have chlorine molecules. And as you remember the Lewis structure, it has 7 electrons. So since it has like 1 odd number of electrons, we call it also an what was it? Free radical. We call it radical. The word radical can slip my mind. So it is a radical. And radicals have odd number of, electrons. Okay, so here we have like 1 here. Or like in general it's 7, we have like 1 non-even electrons. And then the same thing here, 1, 2, 3, 4, 7. Okay. So see, this is the first step. We call that initiation. The second step has 2 steps itself. So you have your alkane, okay, that reacts with one of these chlorine radicals and produces 1 alkyl radical. And again, because it has like 1 electron here, you have 1 here, 1 here. When you break it, you have only 1 electron here. You have alkyl radical plus HCl, right? This hydrogen, with this one, they make, you see that 1 electron here, 1 electron here, they share it, it would be like HCl, right? And in the second step, and then in the lecture, and then also the Khan Academy video that I reference, it gives you like detailed explanation that why, when you break this chlorine molecule, you have two radicals. So in the first step, the alkane reacts with one of these chlorine. In the second step, because you have like so many chlorine molecules, so one of them breaks, and then produces these radicals. The chances are that this radical that is generated here again reacts with your chlorine molecule, another chlorine molecule, and produces RCl, basically alkyl chloride or alkyl halide. This was what I was thinking earlier, right? Plus, again, you see that this R with this one of these electrons here, they form bonds, so you have RCl plus Cl radical. Okay, and this is one question that I asked in exam, and so many students got it wrong. That I said, in which step of free radical chain mechanism we have chlorine radical or chlorine atom being generated? So you have chlorine atom being generated here and also here. So the answer
Just
would be
initiation and propagation.
exactly.
Okay.
I got
Okay.
one right.
Yeah.
I think I just chose propagation.
Yeah. And then the final step, all the radicals combine together, form bonds, and then you have like molecules. For instance, Cl plus Cl gives Cl2, and also radical R, alkyl plus alkyl gives you RR, and then R plus, so all the combinations, one would be ClCl, RR, RCl gives you RCl. So this would be termination. So you should know that for your exam too. And I asked you in which step, for instance, RCl is being generated. So in that case, it would be propagation and termination. Or like in each step, Cl2 is being generated. That is like termination. So as long as you know how to write these.
Would it be initiation and termination, or would initiation not count because it's not being formed? It's just given.
Yeah, just termination,
Okay,
because
yeah.
here, as you said, is given. But if I ask in which step chlorine molecule is being broken, or like forms chlorine atoms, right? It would be initiation. Okay.